Okay, this is section 6.4 in our MathLinks 8 textbook. We're cruising along at a pretty good speed here. And section 6.4 is us learning how to multiply a mixed fraction by a mixed fraction. So what we're going to do in a second is I'm going to teach you how to multiply a simple one, like 1.5 times 1.25. We're going to learn how to do that in just a second. We're not going to do it right away. Before we get to that, we're going to go back to grade 4, and we're going to learn how to, so our grade 4 learning, and it might have been grade 4 or 5 or 6. I'm going to put grades 4 to 6. I don't know what grade it actually happened in. But in grades 4 to 6, probably around grade 4, you learned how to take something like 12 and multiply it by 15. Okay? I think probably around grade 4 is when you learned how to do that. And in grade 4, you learned that there were a couple of different ways to do it. I think the way that a lot of us learned how to do it, or at least the old school people, is you line up your numbers and you say, I have 5 2s. What's 5 2s? It's 10. So you have 0 1s in 10, and you have 1 10 in 10. You say 5 10s is 50, plus one more 10 is 60, or 5 times 1 is 5, plus 1 is 6. So 5 10s is really 50, plus an extra 10 is 60. So the 6 goes in the second decimal place, or second place value, because of its value. Then you say, okay, I'm going to put a 0 here, because this 1 times this 2 is really, what is 10 times 2? And what is 10 times 2? 20. But 1 times 2 is 20. So because we're in the second place value, I put a 2 down there because 1 times 2 is 2, but that 2 really represents a 20 because it's in the second place value. And then I said, what's 1 times 1, which is 1, but I'm not really asking what's 1 times 1. I'm actually asking what's 10 times 10 when I say that, right? Because this is a 10, and this is a 10, and 10 times 10 is 100, or 1 times 1 is 1. So when I put this 1 in that third place value, it actually represents 100, 100. And then I would put a line over it, and I would add the digits up together, and I'd get 180. How many of you know how to do multiplication of two decimals like that? Okay. So most of us know that method. But the other method you kind of learned is that when you have 2015s, you might have learned that just like we did over here with this, if we have 12 15s, then we'll have two 15s, and we will have 10 15s. Does everyone kind of get that idea? Or if I reverse it again, I'll have two 10s and two 5s. Right? This idea can be expressed. Two 15s is really two 10s and two 5s, if I think about two 15s. And 10 15s can be 10 10s and 5 10s. Right? If I think about 10 times 15, I would have 10 10s and 5 10s, or 150 altogether. So when we simplified this, we would have 20 plus 10 plus 100 plus 50. And when we added all those together, we would end up with the same answer of 180. How many of you kind of remember that idea? That when you multiply two-digit by two-digit numbers, you're really having the sum of four different parts. Okay. If you don't remember this part, hopefully it makes sense, right? Because what we're going to do today is we are going to extend that into what we call an area model. So if I take an area and I say the length of this is 15 and the width of it is 12, right? How would I get the area of a rectangle? What's the formula for the area of a rectangle? Length times width. So to get the area, 15 times 12 would be the area. And since we've already done it up here, what's 15 times 12? So the area would be 180, and if these are meters, we'd say 180 square meters is the area. Does everyone understand that idea? Okay. Well, we're going to expand upon this basic area model, and we're going to draw the rectangle again. Maybe what I'll do is I'll bring this over here. I'll bring all of my wonderful drawings over here. Here's what we'll do. I'm going to redraw this rectangle, but instead of making the length a full 15, I'm going to cut it right here. And I'm going to say from this point to this point is 10 meters, and from this point to this point is 5 meters. What's the whole length of that side? It's still 15, isn't it? Right? I've just broken it up into a 10 and a 5. And the width here, I'm going to make this distance from here to here 10, and this distance from here to here, guess what number I'm going to make that? 2. Why 2? Because this length is 12. All right. So instead of having a big rectangle that's 15 by 12, I'm going to have 4 smaller rectangles that are different dimensions. But you all agree that if I call these 4 rectangles in here, rectangle A, rectangle B, rectangle C, rectangle D, A plus B plus C plus D still should equal the area of 180 meters, correct? 180 square meters. They should still be the same if you think about it. So what we're going to do here is we're going to calculate the areas of each smaller square within that 180 square meters. What is the length and width of A in our redesigned? It is 10 by 10. Do you agree? So 10 by 10 is our dimensions. What's our area? 100. What about the length and width of B? 5 times 10. Does everyone see that? So this is 5 times 10. So what's the area of B? 50. And what about C? What's the length and width of C? It's 2 by 10 or 10 by 2, isn't it? Which is what area? 20. And finally, the last one, what's the dimensions of B, or D, excuse me? 5 times 2, good, which is 10. If I add those 4 areas together, what would I get? I'd still get my 180 square meters. Does everyone see that? Okay. So the idea of area of rectangles, 15 by 12, this model of this, what we call this an area model, is the exact same thing as this very confusing part that we did up here, right? It's just a different way to represent the exact same thinking, okay? Now you might be asking yourself, well, what does this all mean with mixed fractions? Well, let's look at that original question I said I was going to give you. 1.5 times 1 1/3. That was the original question we were going to start with. And we're going to try our very best to show you that 1.5 times 1 1/3 can be solved using that red area model. So we're going to make this length right here, the whole thing, 1.5, and we're going to make this distance from here to here 1 1/3. But we're going to break it up. So the first part from here to here is going to be, guess what length? 1 meter. Okay, did you get that? Did I make a mistake? Oh, was it 1/4? Oh, it was too. Oops. Let's change it here. 1/4. Everybody's jumping on me. 1/4. So from here to here is going to be 1, and from here to here is going to be 1/2. So what's this whole length right now? It's still 1.5 meters long, correct? We've just broken it up into 2 parts, the fraction part and the whole number part. And then I'm going to put a line across here, and this distance from here to here is going to be, guess what number? Also 1 meter. And from here to here, it's going to be 1/4 of a meter. Is everyone okay with that? Okay. So what we're going to do next, just like we did in the last one, is I don't know what 1.5 times 1 1/4 is. I don't know the answer. But I do know, based on my 15 times 12, that I can break it up into 4 parts and add them all together, and that will be the same as whatever the product is of 1.5 and 1 1/4. Right, Colin? Perfect. So let's start with area of A. This is a pretty easy one. What is the area of this part of our rectangle? What are the length and width of that? 1 times 1. And what is the area then of A? 1. That's pretty easy. What about B? What's the length and width of B? It's 1/2 by what dimension? 1. The length is 1/2, the width is 1. Anything times 1 is itself, right? Like 4 times 1 is 4, 10 times 1 is 10. So 1/2 times 1 is still 1/2. So we got 2 parts so far. What's the length and width of C? What's the length? 1. And what's the width? 1/4. Well, that's easy too. What's 1 times 1/4? 1/4. Same thing as our last one. Anything times 1 is itself. So I'm going to circle these areas. So now we got A, B, C. And the last one's kind of our hardest one. The length is 1, or is 1/2. The width is 1/4. I'll write it over here. 1/2 times 1/4. This comes from section 6.3. Does anyone remember how we do that? What's the rule for that? Multiply your numerators, multiply your denominators. So what would our area be for D? 1/8. Okay. Now I still don't know what 1.5 times 1 1/4 is, but I know how to get it now, don't I? That product of 1.5 times 1 1/4 will be the same thing as 1 plus a half plus a quarter plus an eighth. So how are we going to add those together? The first thing I'm going to do is I'm going to say, you know what? I'm going to not worry about my whole numbers. I'm going to bring that down. But what I am going to do here, Andrew, is I'm going to add my 3 fraction parts. And in order to add them, Grace, I need to have a common denominator. And what's the common denominator that 2, 4, and 8 share? 8 is the lowest common denominator. So I'm going to rewrite this as the sum of 3 equivalent fractions with denominators of 8. The good news is 1/8 doesn't change, so I don't have to do much thinking for that. What is an equivalent fraction to 1/2 that has a denominator of 8? Well, 2 times 4 is 8, so 1 times 4 is 4/8. A quarter is equivalent to what fraction? 2/8 and 1/8. Now that I have 3 equivalent fractions that share the same denominator, my rule for adding fractions is keep your denominator and add your numerators to give you the final answer of 7/8. So 1 was brought down. The 3 fractions were added together to give you 7/8. So when I combine those together, my final answer is 1 and 7/8. So therefore, because those 4 parts add up to be 1 and 7/8, therefore 1.5 times 1 1/4 equals 1 and 7/8. Okay, that seems pretty complex, doesn't it? Now the expectation that I have for you as your teacher is that you can do that. You can demonstrate an understanding of how to show what the product of a mixed fraction times a mixed fraction is using that fairly complex but not overly difficult model of area model, okay? But good news, there's an easier way to get the answer. Does anyone have a suggestion for what I can do without modeling it, without addition, that makes it much easier to get the answer to the product of 1.5 times 1 1/4? What do you think? Multiplying the denominators and the numerators would work if they were just regular fractions, but because they're mixed, it's not going to work. Nice guess. What do you think? That is the exact answer I was looking for. What we're going to do instead is we're going to change both of those mixed fractions into improper fractions. So what is 1.5 as an improper fraction? How many halves are there in 1.5, Cole? 3/2. Would you agree that that is the improper version of 1.5? Good. And what is the improper fraction version of 1 1/4? How many quarters are there in 1 1/4? Not 4 quarters, that would be 1. Has 4 quarters. 5 quarters is correct. So if we look at this statement and we look at this statement, you should see those as being the exact same thing, correct? But the good news is because we wrote them as improper fractions, our 6.3 method, which is just multiply the numerators, multiply the denominators, is now much easier to do. So if I use that 6.3 understanding, what's my numerator going to be in my product? When I multiply those together, what will my numerator be, my top number? 15, because 3 times 5 is 15. What's my denominator going to be? 8. What is 15/8 as a mixed fraction? The answer I spent all that time and hard work doing, I got much easier, right? So I got the same answer of 1 and 7/8 by just changing the mixed fraction to improper and multiplying the numerators and multiplying the denominators. But that idea of this simplistic way of getting the answer is only one part. The other part you have to be able to do is you have to be able to draw it this way. Okay? Let's try one more. Let's see how well we do. Let's just try one. Let's go with a simple one. 1 1/3 times, let's go with 1 1/5. So what I'd like you to try and do is draw that with an area model. Okay? I'll even help you draw it. So I want you to make a rectangle. And I want you to cut it into 4 parts, A, B, C, and D. Does anyone know which one's bigger, 1 1/3 or 1 1/5? What's the longer one, 1 1/3 or 1 1/5? 1 1/3 is longer. So we're going to make the distance from here to here 1. The distance from here to here, 1/3. From here to here is going to be 1. And from here to here is going to be 1/5. Okay, so what I'd like you to do now is try and find I'll press pause on the video. You guys find the 4 areas for A, B, C, and D and add them together, okay? Okay, that was good. So in YouTube land, that took no time, but in reality, we took about 6 minutes to do this. So we're going to go ahead and try and find the areas to all of them. So remember, 1 1/3 times 1 1/5 would be the area, the entire area of this rectangle. But instead of finding the total area, we're finding the area of the 4 parts that make up that total area, A, B, C, and D. Since A is 1 by 1, its total area is 1 square unit, whatever it happens to be. Since B is 1/3 times 1 or 1 times 1/3 using the commutative property of math, it's still 1/3 regardless of how I look at it. C is 1 by 1/5, which is simply 1/5. And D, I'll bring the work over here, it's 1/3 multiplied by 1/5, which makes this area 1/15. So if I think of the entire area as being A plus B plus C plus D, it can be 1 plus 1/3 plus 1/5 plus 1/15. Now, because we have a whole number here, we're going to ignore that and just bring it down to our final sum down here. We'll wait until we figure out what the sum of those 3 fractional parts are. Our common denominator, or our first multiple, 3, 5, and 15 share. If you needed to do this, you could actually write out your multiples here and go 3, 6, 9, 12, 15, 18, 5, 10, 15, 20, 15, 30, 45. The first one they share is actually the number 15. Right? All 3 of them have 15 as a common multiple. So that is what we would call our first common multiple, or our lowest common denominator. So we're going to use that 15 thrisely with all 3 fractions. 1/15 isn't going to change. Z, what's an equivalent fraction to 1/3 that has a denominator of 15? 5 is right. Good stuff. What about what's an equivalent fraction to 1/5 that has a denominator of 15? 3. Now, once we have those equivalent fractions made that all have the same denominator, my rule for adding fractions is keep your denominator. We're going to keep that denominator and add our numerators. And our final answer is 9/15. Is 9/15 just out of curiosity lowest terms? No. What can you divide, Grace, what can you divide into 9 and 15? 3. And if I reduce this by a factor of 3, then it's going to be, oh, I just erased that. I don't know what happened there. It's going to become 3/5, isn't it? 9/15, when reduced to lowest terms, will become 3/5. So all of these 3 fractional parts add up to become 3/5. Bring that down, add that to my whole number. My final answer is 1 3/5. Now, what's the easier way to do that? What's the easier way to get that answer of 1 3/5? What would you do? Yeah, we're just going to change those 2 fractions and see if we got, so we had 1 1/3 and 1 1/5. Let's just see. So 1 1/3 times 1 1/5 as 2 improper fractions. 1 1/3, how many thirds would there be in 1 1/3? There's 4 thirds. 1 1/5, how many fifths would there be? There'd be 6 fifths. Remember yesterday what I taught you how to do if you were multiplying 2 fractions? What can you do before you multiply those 2 to make your life easier? You could cross-reduce. I'm not going to do it yet, but I'll show you in a second what you could have done. What we're going to do is multiply our numerators, multiply our denominators, and we'll end up with 24/15, which is 1 9/15, which is equal to 1 3/5. Now, just as the last part of this video, if you did want to cross-reduce, remember what I said last time, is that if we swap these numerators, it would not affect the overall product, because instead of being 4 times 6, if I swap those numerators, it'd be 6 times 4, but it's still going to be 24 regardless of the order of those numerators. So what we're going to do is we're going to cross-reduce. So if 6 was over 3, what would that reduce to in lowest terms? 2 over 1. Would you agree? And then if I multiply my numerators, I get 4 times 2 is 8. 1 times 5 is 5. And that gives me 1 3/5 without having to reduce that fraction in the end.